is the while the exam is performing. Okay. Uh, and then what else? Okay, I think that's all from my side. Do you have any question before we starting?
We're gonna have extra 15 minutes like last time.
Yeah, I think this time also I will give you extra 15 minutes. So we're gonna start the exam exactly 11 o'clock, and then by 12:30, you need to send your exam. Okay, back to me.
Thank you.
Okay. Uh, okay. Okay. So so today's lecture I'm not going to record. So it's you're gonna ask a question. Okay. So, the exam, as I mentioned, is mostly covered from chapter 8 to chapter 11. Okay. And then some of the knowledge from the previous chapters require to understand some questions, but mostly is from the chapter 8 to 11. Okay. So in the chapter 8, we're going to start with the bipolar junction transistor. Okay. So in the BJT is that is one thing is obviously when we talk about any device, we come with the energy band diagram. Okay. So for this question is basically asking about is N plus PN silicon this BJT. And then question A asking about the energy band diagram. Okay. Keep in mind is when you draw the energy band diagram need to show the relative this doping concentration. So as you let me put down this is N plus P N BJT. Now is when you draw the energy band diagram at the thermal equilibrium. So always when you draw the diagram at the thermal equilibrium, your EF first need to be constant throughout the device structure. Okay, that's the you have to do always, right? At the thermal equilibrium. Now we're gonna draw the energy band diagram. N plus means that your conduction band is close to the EF. Okay, so emitter side, if I draw the N plus, let's say this is the EC, okay, close to the EF. And then let's say if we draw the EV, we can draw it this way, right? It's in the emitter side. Now, if you look at the collector side, this one also is N, okay? But compared to this emitter side, and this one is lower doped. Okay. So to represent this one is lower doped, the separation between the EC and EF is larger than the this emitter side. Okay. So in here is collector side is EC should be is separate more than this emitter side. Okay. And then you draw the EV in here. So obviously, as you know, is EI is kind of in the middle, and then still this one represents the N-type, the semiconductor. Okay, and then the P side is now P side is EV is closer to the Fermi energy level. And then ideally, as you know, if we consider the fabrication step, the base side of this P doped, the doping concentration, this one should be a little bit larger than the collector side. Okay. So when you draw the EV, in the base is going to be close to the EF, and then you have EC is located here, right? Okay. And then if we connect them all together, we're going to expect that the energy band diagram going to be something like this, okay, at the equilibrium. Okay, so that will answer this first question. Okay. Now, in the second part is the device operate in the active region. Okay, the active region means that the bias between the emitter and base, this one is a forward bias. Okay, and then collector and the base, this one is a reverse bias. Okay. The forward bias means that in the p-n junction, this one is a p side, you apply the more positive bias compared to the n side. Okay. Reverse bias is opposite, right? So just to keep in mind that one, then now is we're going to apply the bias into this energy band diagram. Okay. So first, emitter and the base is in here between these two. Okay. Now emitter and base is a forward bias. Okay. So which means that the P side is more positive bias compared to the this emitter side. Okay. So now because base might be the base is connected between the collector and the emitter side. So let's say just to keep the base in this level, and then we're going to just move the corresponding emitter side this energy. Okay, so which means that the emitter side is more negative bias compared to the base. So negative bias means that the energy, this one will be shifted. Okay, so for example, is EC is a shift, okay, then the EV also is going to be shift, okay, EF also is going to be shift, okay. Now, if you connect this one to the base, okay, and then this shift amount is Q V emitter base this bias, okay. So that is a forward bias between the emitter and base. Now, collector and base is a reverse bias. Okay. So which means that in the N side, okay, reverse bias means that the N side is that you apply the more positive bias. Okay. When you apply the more positive bias, the energy going to be shifted to the downward, right? So new energy is a shift, is downward, everything. So if we consider that one, is now, is you can see, is for example, and then you have new EF, okay? And then this amount of change in here related with the QPC amount of change, okay? So that way is you can answer the question B. Okay. So everything clear for the energy band diagram?
So Professor, in the inverse, in inverse active region, it will be the opposite, right? Like the N plus side will go downwards, and then the N side will go up, right?
Yeah. It's just to keep in mind is that whether this is a different region, inverse active region or active region, just to keep in mind is that this is forward or reverse, right? And then is which energy is go up or down. I think if you just remember that one, then whatever is condition, you can answer those questions.
Okay, thank you.
Okay. Okay, so that's
Professor, can you quickly go over part B one more time?
Oh, Amadi, can you
Just like
say
an
that
overview of
again?
it. I'm saying, can you quickly do an overview on part B one more time? Yeah.
Overview of what?
Part B, like one more time, please.
Part B. Okay. 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 First of all, you understand how to draw the energy band diagram is at the equilibrium, right? Okay. So assuming that you can draw the energy band diagram at equilibrium, that represents this one, okay? And the EF is constant throughout the device structure. Now, as I mentioned, is that part B is specific this operation condition. So active region, this one is specifically emitter base is forward bias, collector base is reverse bias. Okay. The forward bias means that the emitter base PN junction, in the P side, you apply the more positive bias compared to the N side. Okay. Reverse bias, PN junction now is P side is more negative than the N side. Okay. So only thing you have to keep in mind is this condition. Okay. Whatever this region is applied. Okay. Now, second one you have to understand is that when the energy band is forward bias, okay, the energy is go down. Reverse bias, energy is going up. Okay.
Professor.
So you just only need this one. Okay, Amari,
Professor.
do you have a question? Yes.
Yeah, you said when VEB is in forward bias, the base is more positive, and then for a reverse bias of VCB, the base is now more negative.
Reverse bias is this is which is PN is think about is that the emitter base is this one, right? So this is a P and this is N, right?
Yeah, the P is the base in the scenario.
Yeah. So is the forward bias. This one means that the P side is more positive than the this emitter side. Okay.
Okay. Makes sense. Thank you.
Yeah. Okay. So that's basically it for this question. Okay. Why base P is not shifting? Okay, it's your choice. Is that because is right now is to draw this one is kind of simple. I decide to base is just not shifting. Okay, because I need to draw the emitter and the base, and then later on is the base and the collector. Okay. If you decide to draw that, let's say emitter is not shifting, then you have to draw everything or change it. Okay, so either way is fine. So I mean, is that answering your question? Okay, so either way, as I mentioned, energy band diagram is we are just looking at the relative difference between the emitter base and collector. So if you draw, for example, if you keep the emitter is keep this way, then base going to lower, okay, and then the collector and base is further lower, right? So you can draw this way too, okay, or you can keep the collector side is in the same level. Okay. Any other question?
Professor,
Yes.
I'm sorry to come back to the topic, but if you have like a battery connected to the emitter side, right, and it's in forward bias, wouldn't you be connecting the positive part of the battery to the emitter side? So wouldn't it be more positive on the emitter side compared to the base?
If you apply the forward bias, okay, emitter and base, Okay. The meaning
Yeah.
of the forward bias is a base. In this is a base is a P, right? So P is a higher potential than this emitter side.
Is that just because of the charge in general? Because it's an N plus P?
No, that's the definition. We always have the p-n junction. So if you have p-n junction, our definition is forward bias means that the p side is positive than the this n side.
Okay.
Yeah, it's a definition. Is people define this way as we call the forward bias. So all the concept understanding is we follow that this definition. Okay. Okay, then that's good. This one. Okay, 8.20. Okay, this one is again. This is n plus pn PJT. And then this case is PJT operate in the inverse active region. Okay. And then the first is it asks sketch the minor carrier distribution in the base and the emitter and so on, right? So if we just split, for example, is let's say this is emitter and this is base and let's say this is collector. Okay. Now this is n plus p n diode. Okay. In the n plus minority carrier going to be whole, right? So let's say if we have at the thermal equilibrium, P O N is let's say located in here in the emitter side. That's the minority carrier in the emitter. In the base side, minority carrier going to be electron, and then this concentration going to be higher than this emitter side minority carrier concentration because it's n plus pn diode. So if we just at the thermal equilibrium, if we draw, then that represents the NOP. Okay, so same way collector. If we draw, this one is PON in the collector side. Okay, and that's the kind of minor carrier distribution. Of course, I think I forgot to get rid of this depletion region. Okay, so this is only in this neutral region, minor carrier distribution. Okay, so this is at the thermal equilibrium. Okay, now our question in here is that we have inverse active region. Inverse active region means that between the base and collector is forward bias, and then emitter and base is reverse bias. So which means that emitter and base when is reverse bias, carrier concentration, minority carrier concentration is lower than their thermal equilibrium value. Okay. So let's say is a depletion edge located somewhere in here. Base and collector is forward bias, so there will be is that located in here. Okay, their minority carrier concentration. And then, as you know, is this one is naturally, if you go in the deep layer, you're going to have this kind of distribution between in the emitter side and collector side. And then base side is if the base width is typically is very small, then we can draw this one is linearly changed, something like this. Okay, so this one is now represent your minority carrier distribution for this particular transistor. But keep in mind is that the level of this one represent your doping. Okay, so you have to represent this one correctly. It's same way like when you draw the energy band diagram, the relative the gap between the conduction band or permeability level that need to be properly is distinguished, right? The same way is you have to distinguish this one like this, okay? And then this one is inverse active region. Okay, Amadit.
So, Professor, in the inverse active region, both the EB and BC are both in reverse bias, and all the minority carriers drop in all three sections?
EB, this one is a reverse bias. BC, this is a forward bias.
Oh, it's in forward bias. Okay. And then, in which region did the minority carrier charge increase? In the base?
As you can see, is that when you reverse bias, the minority carrier concentration is lower than your summer equilibrium concentration. So you have this kind of drawing. When you apply the forward bias, minority carrier concentration is increased from your summer equilibrium value.
Okay. Thank you.
Okay. Mm-hmm. So,
Professor? Yeah.
Yes.
So you see this like depletion region here? So you say one is bigger than the other one, right?
Yes.
Okay, so in this case, the biggest one gonna be like this one between the emitter and base, right? And then the smaller one is the base collector, right?
Bigger of what? You mean the carrier concentration or?
No, I mean like you see this space between the emitter and the base.
Okay, base.
The
Between
space.
the emitter and base, reverse bias. Okay.
So this space here between the emitter and the base is bigger, right? Than the space in the base collector.
You mean the depletion region? Oh yeah. This one, I think depletion region is not correctly represented. It's a reverse bias. Suppose this is a bigger than this forward bias. Yes.
Oh, okay. Thank you.
Okay. Any other question?
Professor, if it's gonna be P and P, then we how much it's gonna be different?
P and P?
Yeah, instead of NPN.
So P and P, this one minority carrier, this one going to be now is electron. So NON, okay, and then this base is PON. This one is NON, and then the level going to be similar.
Oh, they still have the same kind of distribution, only change to the
minor
instead.
To the
Yeah.
opposite. To the opposite charge.
Yeah.
Okay.
Yeah. Okay. So that's is question A, first one. Okay. Second one is now is this one asking about this the alpha this value. Okay. The alpha value, this one related with injection efficiency, and then the base transport factor. Okay. So base transport factor is related with this alpha, this gain parameter. Okay. Now, injection efficiency, this one related with that. For example, if we look at the active region, it represents your emitter current for the majority carrier current, and then you look at the total emitter current, which means that the majority carrier current and then the minority carrier current. Okay. So now, as you can see, is that as you have the smaller this minority carrier current, okay, then this injection efficiency going to be larger. Okay, as you increase the contribution from the minority carrier current, then this injection efficiency is go down. Okay, so based on this concept in here, now is when you compare the this alpha R represent the device operate in the inverse active mode. Alpha F represent is same way forward active mode. Okay. Okay, Amadip, do you have a question?
Yeah, Professor, another question. So there's only two ways, right, to lower the minority charge carrier, either through the biasing or initial doping, right?
Initial doping. This one is not asking about the bias.
No, I'm just saying in general, like regardless of the question, like just in general in semiconductors, right? The only way to affect the minority distribution is either through the biasing or the doping, right?
Yes, that's correct.
Okay.
Okay. So now inverse. So as I mentioned, is this is M plus Pn PJT. Okay. The emitter side is doped more than the other is a collector and then the base. Okay. Injection efficiency. When you look at this one, when this one operate in the forward active region, okay. In this case, the minority carrier contribution, this one is small, so that your injection efficiency going to be large. Compare to the injection efficiency when you have the inverse active region. Inverse active region is that in the opposite direction, right? We apply the forward bias between the collector and base, and then the emitter base reverse bias. For this case, is that because the collector side is doping is lower, okay, so that your minority carrier, this one is much higher. So when you look at the injection efficiency, this one going to be small. Okay, so that's the reason is that when you compare this alpha F and the alpha R, you're gonna have alpha F going to be large. Okay, so the correct answer this one is related with the natural is doping concentration difference. Emitter side is much highly doped compared to the collector side. Okay. Okay, so then we're gonna go to the chapter 9. Okay. So chapter 9, we're gonna start to look at the Michael, do you have a question?
Yes. Basically, in the
Okay.
previous question, can you please go over one more time the B part?
Okay. So B part asking about that is why this alpha F is larger than the alpha R. Okay. So first of all, definition of this one in the book is the alpha R represent is when the device is operated in the inverse active region. Alpha F is the device operated in the forward active region. Okay. And then if you look at how this alpha R, alpha F, this alpha parameter is calculated, this one is proportional to the injection efficiency. Okay. So injection efficiency related with inversely with minority carrier this concentration. Okay. So minority carrier concentration in the collector side, this one is larger than the emitter side. So that's why is that we have this kind of result. Okay.
Okay, thank you, Professor.
Okay. Okay, so chapter 9, we're going to start the non-ideal characteristic of the BJT. Okay. So this particular case is that the BJT is operated in the active region. Okay. BJT operated in active region, and then the base doping is given, collector doping is given, and then the base width is, let's say, initially for this case is 1.2 micrometer. Okay, and then the emitter base forward bias is you have 0.6 volt is applied in here. Okay, and then first question is that now if you change the base, if you change the voltage between the collector and emitter from 1.5 volt to the 6.5 volt, okay, how much is the base width going to be changing? That's the first question. Okay, so if we draw this case is systematically, okay. Let's say if you have emitter and base, you have a base and collector, you have depletion region. So let's say this is the base region, and this is emitter, and this is a collector region. Okay. Now, emitter and base, this one is forward bias. So in here, base is P-type semiconductor. This is N-type, and this is N-type. Okay. Now, in the forward bias, this one is fixed, right? We do not change this base and emitter voltage. This is fixed, okay? Fixed with 0.6 volt, okay? Now, collector and the base, this voltage is going to be changed, okay? This one going to be varied because we change the voltage between this collector and emitter voltage, okay? So in here is if you look at collector and emitter voltage, this one voltage is, you have, is basically, when you measure this one, you have voltage between the collector and base, plus this one is base and the emitter, this voltage, right? So that represent this voltage, collector and emitter. Okay. Now, base and emitter, this is a fixed, right? We fixed this voltage with the 0.6 voltage. Okay. And then we change the voltage, this one is from 1.5 volt to the 6.5 volt. Okay. So now, then, collector and base voltage is going to be changed. Okay. For this case, collector and base voltage going to be changed from the, let's say, 0.9 volt, okay, to this one is 5.9 volt. It changed, right? Okay. So that's the case in this case. Okay. Now, for this case, as you know, as we apply the more negative voltage between the collector and base, you expect that the depletion region is going to be changed. Okay? Let's say this is the initial depletion region. When you apply the more reverse bias, depletion region in the base is going to be changed. Okay? And then that one effectively change this base, the width. Okay? So in this question, first one is asking about then how much change it happens in the base. Okay. The change in the base is, as you can see, between the base and then the collector, this is a PN junction. Okay. PN junction, you apply the reverse bias, is that from 0.9 volt to the 5.9 volt. So the difference in here is that you apply the 5 volt, right? Reverse bias more. How much depletion happens in this base side? Okay. That's the case, is the first question. Okay. So this one simply is, this is a PN junction. Okay. In the base side is, you look at this base XP, this change when you apply the more negative bias. Okay.
Professor, what did you write over there?
Oh, already? Yeah.
Above VCB, above VCB, you have an arrow going upwards. What does that say? 15?
Oh, no. This
You
is
know
this is a 5 volt difference.
Oh, okay.
It's from 0.9 to 5.9 volt.
Okay.
Yeah, it's 5 volt, right? Okay. So now is everything is going into the very simple question, right? So this is simply is a PN junction between the base and collector. Okay. If you have more reverse bias, this 5-volt difference, how much depletion going to be changed in the base? Okay. So that's the question is in the first part. So can you understand the question here?
So, Professor, we're just gonna find the basically the change of the 5-volt difference, basically something.
Yes,
Like,
because that's the asking in here, right?
Yeah. So we're just gonna use the 5-volt with the similar equation from our basically first midterm.
Yes, it's just in the PN junction, and then you are looking at in the P side, the depletion region change when you apply the 5-volt to this the difference, right?
Mm-hmm.
So that is this question, first question. It's nothing more.
Professor, do you remember the equation you used for the width?
It's I think it's in the book. So yeah, it's in the book. So you don't need. I don't remember exactly. It's a long equation, but I think if I just remember, it's something like this. It's let me just write down. It's kind of xp. This one is there is some parameter. This one, 2, and then there is I think a q. It's na plus na multiply nt, and then this is 2 times epsilon, and then the na and d, and then in here is the voltage is I think this is a VBI minus VA, something like that.
And
Okay,
the top
no, that looks-
NA
that looks
plus
familiar.
80.
Target, yeah, target is probably, and this is a multiply, right? Yeah, that's.
And this way, and Professor, sorry, and the voltage we have, which is VBI minus VA, we're just gonna put the 5-volt basically.
This one is yes, because that's the difference is we will get, right?
Yep.
So because this one is not asking about the absolute value, it's asking about the change.
I see.
Okay.
So, Professor, in our case, VBI minus VA is just the 5 volts.
That is, you can put in here is that the VBI is that you actually calculate, right? So using the correctly this equation in here, right, is that you can put the VBI, and then the VA, this one is 5-volt difference,
Okay.
right? Because that is a VBI minus VA. It is a correct equation.
So, Professor, you said is VBI minus the 5 voltage difference we have?
Yes, so this one is a reverse bias, so it's a plus 5-volt, right?
Plus, well, yeah, plus 5, yeah.
Okay. Then you can actually get this delta XP change, right? Okay. So that's is basically is that if you put this one, now from there is that initially WB is at the 1.2 micrometer. Okay. Then if you put this one is basically WP2 is going to be such a number, right? So that's going to be this change in the base width. Okay. But anyway, the change is going to be this one. Okay. So that will answer the first question. Okay. And then the second question, this one, is that now we look at the collector current. Okay. So collector current in the active mode, if you write down this one, it has a formula. Okay. It has a formula is something like this. QADP POWB exponential, and then there is a QVEB over KT, something like this. Okay, so we have this collector current is following this one. So in here is that initially is a device operate VEB is given in here. Okay. QKT is you can have, so you have number this one. Okay, and then the doping everything based on the order number is you have initial this collector current, right? Now you have changed this WB when you apply the bias in this way. So from there is that you can calculate the is change of this collector current. Okay. And then that collector current is that, as you can see from this equation, is inversely proportional. Okay. So in other words, if you look at this one, is if you compare the IC initial one with the IC2, okay, this one is inversely proportional, so which means that this one is WB2 divided by WB1, right? So using this one is now is you can actually also calculate the corresponding change in the collector current. So this one case is that this one is that you can actually calculate from this one, and then you can have a delta IC change, right? So that will answer the second question. Okay, let me speed up a little bit because we need to cover lots of things. So 9.2. This one is now is a similar question like in the previous, okay, but this case is that the emitter collector is doping is given, but the base side the doping is not given, okay. And then initially is that this is also active region, is operate in the active region with the base and emitter is a certain bias, and then collector and base is also reverse bias 5 volt in here. Now, the question this one is that for the all the same, we increase the collector and base reverse bias is 10 volt, okay, from the 5 volt. Okay. Then the result was that now is we see that the minority carrier diffusion current in the base is increased 20%. Okay. One thing is you have to understand is that the minority carrier diffusion current in the base, that's the meaning of the collector current, collector hole current. Okay. So collector hole current is increased at 20% is more. Okay. So basic concept, this one is the same as previous. You have emitter side, base side, and collector side. Okay. Emitter base is at the forward bias with 0.7 volt in here. Okay. And then collector and base is initially it was 5 volt reverse bias, but now is we increase this as 10 volt. Okay. So when you increase this one, as you know, effective this base width is going to be decreased. Okay. So this decrease is create the slope of this base region minority carrier, so that that increase, as you know, is this minority carrier diffusion current. Okay. And then for this case, is asking about the base doping and the early voltage. Okay. So this one is also is the same. Is that we're going to use the same approach. Okay, so to calculate this one is we know that first of all is that the current. If we compare the, let's say, initial current with the discharge current, this one is following with the base effective width. Okay, so which means that let's say if we put the base width in this way, okay, it will have this relationship like in the previous question. Okay. Now the clue is that the second this one, the current, this one is a 20% increase. So which means that in the formula we can put the 1.2 multiply IC1. Okay. And then the initial base width, this one is 0.6 micrometer. Okay. Now, from this equation, if we do this one, is the new base width. This one supposed to be is 0.5 micrometer. Okay, to satisfy this equation. Okay. So that means that now in the depletion region change in the base side, okay, so this one is still XP in the base side. The change in this one should be the 0.1 micrometer, okay, to meet this condition. Okay. So then, as you know, is we're going to use the same equation, is XP, okay, and then the change of this voltage is a 5 volt change, right? So then over there is you have to have the equation this one. Again, XP is that I think Khalid put the equation there. Okay, you have this equation with there is a doping. Okay, the doping this one is we are talking about that the base doping is Na, and then we have collector doping is in here is DC. Okay. So then you have the one equation in here, and the second equation in here is that you have the VBI. Okay, VBI is between the base and collector. This one is also is KT over Q, and then RM, and then you have this collector doping. Okay. And then you have this base doping, DC, and then the Ni square, right? So now is that you have these two equations in here, okay? And then if you correlate these two equations, from there is basically you can calculate the doping concentration is N. And base doping concentration, Na. Okay. Michael, do you have a question? So basically, this question is similar to the what asking in the before. Okay. Okay. Second one is early voltage. Okay, Amadi.
You had a question. You know how like for the field effect transistors, right? The gate is usually what controls the channel, right?
Yes. Yes.
So for BJTs, it's the base current. That's like the majority.
It depends on the which mode is you're gonna use, because sometimes we use as a common emitter, common base, or common collector.
Oh, so whichever one is common to, that's the majority factor?
Because this one determines that which one is input and which one is output. So input current is at some case is that the input current is at IB, some case input current is IE.
Okay, but collector, would the collector ever be the input?
Collector is that typically this is output current we are looking at for all of this one. If you look at
okay, I'm just saying in general, like would there ever be a scenario where we would have the collector as the input or no?
In the general use, no.
Okay.
Okay, let's back to, yes, Michael.
Professor, so in case in the question is not specified which kind of BJT we're using, what should we assume? Should we use a common emitter, common collector?
Oh, it should be. Is if the question is that related with this, right? Then it should mention is that the BJT operate in the common emitter or common collector and so on. Because typically this one is that either you're going to use this one as the amplifier or you're going to use a switching device.
Mm-hmm. Yes.
So in the emitter part, amplifier, whether this one is used a common emitter, common base, common collector, or is it used different. So.
Okay, I see.
Yeah. In any case, that should be mentioned.
Okay. Thank you, Professor.
Okay. Okay, let's go back to our, I need to cover everything. Okay, so second question, this is a rather simple, is that you may remember that we have, when the only voltage is happen, is a collector current related with your is output, this voltage change, and then there is a relationship is showing that some kind of this kind of relationship. The current is that increase as we increase the output. Okay. Over there is that now this point we define that this only voltage. Okay. Now for this one is that let's say if we have different bias in the, let's say this is a VCE1. Okay, and then this is a VCE2. Okay, VCE1 is created, let's say IC1, and this is IC2. Okay, so from there you're gonna have relationship is IC1, and then divide by the VA plus is a VCE1, right? This one should be equal IC2 VA plus VCE2, right? It's because the slope needs to be same. Okay. So basically, this question asking about whether you can understand this relationship. Okay.
Professor,
So,
does the
in
first
this
one say
question-
VCE1
CE1.
for the first equation? Oh,
This
VCE1.
one.
Okay.
Right. Okay. So, and then in here is a 20% increase. So, which means that this one is at is 1.2 times IC1, right? So, is from this formula now is you can calculate the VA, right? So this one is nothing much. Just whether you can correctly formulate this equation. Okay, let's move fast. Okay, 9.4. This one is punch through. So punch through is, as we discussed, that when the reverse bias active region, device operate in the active region. Okay, as we increase the reverse bias between the collector and base, the depletion region in the base is going to be increased. Okay, and then when that depletion region is the same as the increase of this depletion region, okay, then now its device reaches to the punch through. Okay, so basically, first one is that asking about punch through voltage. Okay, to calculate the punch through voltage, basically you're gonna use this formula in here. Okay, so XP is the same way. Is in the chat is mentioned. You have formula. Okay, and then over there is you have VBI minus VA applied voltage. Okay, and then typically when the punch through device reach, VA is much larger than the VBI. Okay, so if you calculate that way, then you can actually calculate the VA value in here. Okay, and then that one is we define that the punch through voltage. Okay, And then the second question is that when the device reaches the punch through, what will be the average value for the electric field? Okay. Sorry. So this one is that you have voltage, and then the average this base width is defined by this value. Okay. So then you can have electric field. Okay. And then you know that when you answer all the question, always you need to put the unit. Okay. Okay. Whether this unit is a voltage per centimeter or voltage per meter. Okay. Based on there is the value going to be different. Okay. So that will answer the big question. And then the last one, this question is that, okay, to increase the punch through voltage, obviously base doping can be increased, right? Because the base doping is increased, then this depletion width in the base is much slowly changes is as you increase the voltage. Okay, so but when we increase this base doping, is we have some problem in the BJT. The problem this one is that again is that when you increase the base doping, your injection efficiency going to be lower. Okay, okay. Now this injection efficiency is lower, then your gain in the BJT also getting lower. Okay, so that kind of is circuit parameter is also is kind of degraded when you increase the doping. This one. Okay, so that need to be is answered in here. Okay, now we go to the chapter 10. In the chapter 10, we're going to start to discuss about JFET. Is 10.4. This one is asking for is a very specific case in here. Okay. So the first one is this is let's see. Just 1 second. This is N channel. Okay, N channel JFET, N channel JFET. Okay. VBI is that you can calculate from the is a KT over Q, same the equation, right? With the doping. Doping is you have is P plus in the gate, and then N is in the channel. Okay, so that will answer this built-in potential. That's it's okay. It's nothing changed. And then second one is that the value of the VG is called the pinch up when we have the VD is 2 volt. Okay, so the situation this one is, as you know, the channel this one is VD. This is let's say grounded. Okay, and then in the gate is you have VG. Okay, and then this is a P plus, and then this is N. Okay, now in the drain, you already have the 2 volt is applied, positive bias in applied. Okay. Now between the drain gate and drain, you apply the reverse bias. Okay. So in other words, in the gate you apply the more negative voltage. Okay, to change the depletion region. So as you apply the bias, reverse bias, depletion region is going to be changing. And then at some point, when the depletion region is touching each other, okay, that point is that you're going to have the pinch up. Okay. So consider this one is that now you're going to have a formula is that when the W, this is a channel, this width initially, when this one is equal to the is your depletion width is the same, is a similar, is formula you have there, right? In this one is we are looking at in this case we look at the XN side, okay, N side this one, and then this change is equal to the channel width. Okay, at that point you're gonna have the pinch up happens. Okay, so now if you calculate this one in here. Is that you can calculate. Okay, Amadit? You have a question?
Yeah, Professor, at pinch off, is the drain current 0 or is it at saturation?
No, is pinch off means that the the depletion width is a completely closed channel. So in other words, is if you look at this question in here, the A, this one is a channel width. Okay, when the channel width is equal to your depletion width, at that point, this device reaches the pinch off.
Okay, but what does that do to the drain current?
It's not due to the drain current. It's related with the
No.
voltage.
Okay, I understand that. But I'm saying, does it do anything to the drain current at all? Like, does this like have an effect on the drain current?
Drain current will be saturated at that moment. ID
Okay,
is
okay.
reached to the saturation when the
Okay.
pinch up happens. Yes. Okay, Michael?
Professor, so when VD equals 2 volts, can we say that VD equals V saturation?
You can put that one is that you put the VD is that the VD saturation. Yes, it's correct.
Okay.
You put the because that moment you have the saturation. So in other words, as there is a relationship, right? I think it's pinch up voltage is a VD saturation. I think it's a
VBI.
VBI minus VG, right?
Yeah.
And so you have this relationship.
Okay.
Okay. So basically, is that this one asking about is go back is that then we look at first you need to formulate the channel width A equal to the depletion width at that moment is pinch up happens, and then over there is that you have VBI minus VA in the PN junction typically, right? VA is that the voltage. This one is that voltage between the gate and then the drain side voltage, right? So for this one is VD is already given as the 2 volt. Then you can calculate the VG, right? So then that's the answer for this VG value. Okay. Now,
Wait, Professor. I don't-
Okay, Genesis.
I still don't understand. So we are comparing W with what?
W with the channel width.
With 0.3 micrometers?
Channel width is going to be same. Is what is the A in here? Let's see. The A is 0.3 micrometer.
Okay, so we are comparing W with that, right? And here PA is PG minus PD.
Okay.
Or okay, I don't. It's okay. I just have to read more. It's okay. Thank you.
Okay. But you can understand in here. It's nothing difficult to understand. Is first of all is you accept this one, right? The question you're asking this one. The channel is initially A in the JFET, and then pinch up this width need to be same as the depletion width. Because at that moment is we call the pinch up happens. And then depletion width is related with your applied bias. So we just calculate the applied bias to get the A.
Professor,
Yes.
so VD saturation is given, right? That's the 2 volts. VBI we calculate using the old formula you gave us, and then VP we just calculate using the same A because you said AW.
Yeah, you can calculate that way. Yes.
Okay.
Okay. But this one is even, you don't need to calculate the VP in here. As I mentioned, is VA is we define as VG minus VD, right? And then VD is a given. So if you plug in this one, you can get VG. Okay. That's this one.
But
And
don't you
second
need VA
question
though?
is, huh?
Don't you need VA though if you want to calculate it that way?
Yeah, VA
Because you're saying
is
VA is
that,
equal to.
VA is the VG minus VD. In the PN diode.
Okay, so what's VA in this case then for the problem?
Huh? Huh? What's the
What number did you use for VA for this case?
VD?
No,
Or
for
what?
for VA, what number did you use for this scenario?
VA? VA
For VA, yeah.
This number. VG minus VD.
I know, but you're trying to calculate VG, right? So to calculate VG, we need to know the other two. So VD is
Yeah,
given,
VD
and
is
then
given.
oh VBI. Okay, got it. So I'm saying for VA, you just use the VBI because VBI has to equal
No.
VA.
VBI
Pinch off square.
is minus VA. This is going into the equation in the W, right?
Okay, Professor, I have a question. So VBI minus VA, is that equal to 0 in the pinch?
No. The pinch up is that the channel equal to the W. That's the pinch up.
Okay.
Okay. Okay. I think Khalid he put all the equation there. So thanks. Okay. So that's in here. The C is now this is a general question. Okay. For this case that they didn't give this A in here. Okay. Now this one is asking about is that how W going to be changed, depletion risk, when you apply this bias. Okay. So then if you just put this number in here, then from there you can get the W, right? Okay. And then initially channel as A. So A minus W, this one represents the width of undepleted channel. Right? So that's the question for C. Okay, let's move to next. Now it's chapter 11. We're going to start to look at the metal to semiconductor junction. Okay. And then first one is 11.1. This is, I think, straightforward. This one is Schottky barrier height. Okay. And then, especially this one is N-type silicon. Okay. And then the doping silicon is given, metal work function is given, and the silicon electron affinity is given. Okay. So, if you look at our class material, the Schottky barrier height is looking at in the metal semiconductor side. The barrier height is we can calculate using this formula, right? In other words, you may remember that in the drawing, it's something like this. So EC, EF is EV, right? So we are talking about this one. This is a barrier height, okay? And this one we calculate using this equation. So this one is given, this one given, so you can calculate this one. And then the VBI, this one is, we define the VBI in this metal semiconductor junction. So VBI is obviously, you can calculate this barrier height minus the difference, this energy. That gives us that VBI. And then let's say if you put that one is P, okay, then using this one is you can calculate. That gives us that this Q VBI. Okay. And then how we calculate this one for the semiconductor? As you know, we use the KT over Q, Rn, and then the Nc, and then Nd. This is doping in the semiconductor. Nc, will be given. This is a material parameter, represent this density of state in the semiconductor. Okay. And then this particular case, this one Nc is at, I think, 3.22 times 10 to 19, per square centimeter, something like that. Okay, yes. Or 2 point, it will be given. So for the
Professor, that's the charge density, right? The conduction band?
conduction band, yes.
Okay.
Okay, so that will answer these two questions in here. And then this one is, this is slightly different. Now is, let's say you have n-type silicon, and then metal opposition is 4.3. Okay. In here is asking about at the zero bias. Okay, zero bias means that this is a thermal equilibrium. Okay. In the absence of a space charge region at the semiconductor, which means that if I just draw EF at the thermal equilibrium, n-type, you have a case of this one. So there is no depletion happen in the semiconductor. Okay. And then for this one is asking about the doping concentration in the semiconductor. So this one is that to answer this one is, you can see this barrier height, this one, the barrier height, this one is the same way, metal work function minus semiconductor is this one. Okay, this one needs to be equal to the difference, this one. Okay, so let's say if I put this one as D, that is same. Okay, and then this one is same as is a KT over Q, and then Rn, and then you see the Nc and then Nd. Okay, so that will answer this Nd for this question. Okay, and then last one. Okay, last one is this is N-channel mass FET. Okay. N-channel mass FET, and then barrier height is given, and doping is all given. Okay. So first one is a pinch off voltage. So to calculate the pinch off voltage, we just use it's the same way. Is that the equation in here. So VP is N-channel device, is you have a formula, right? A square Q and D, and then 2 epsilon, right? And then this is a gallium arsenide, so you're going to use epsilon. This one is correctly here. It's epsilon R, epsilon 0. Other than that, is everything is all given, so you just use, and then you can calculate the pinch-off voltage. Threshold voltage, this one is VT, so we define that VI minus VP, right? Okay. And then to answer this one is you need to calculate the VBI. Okay. VBI is that the same way is we can calculate like before. Okay. So we can calculate the VBI. Okay. So then from there you can calculate the VT, threshold voltage. And then if you calculate this one, is that VT, this one is in the N channel, is negative. So this one represents the depletion mode of the device. Okay, okay, Michael, is there a question?
Professor, VBI in this case is the barrier height, right?
This is the VBI is in the barrier height from the semiconductor to the metal.
Okay, so basically in this case it's given and it's 0.9.
So is it given? Let me see.
Yeah, it says that.
Oh no, it's not given. That's the metal barrier height. So you have this one is at in the metal side is as we define is a barrier height. The semiconductor side, this is a Q VBI. This one you need to calculate that this one minus the difference, this one EC and then EF. for the given doping, right?
Okay, I see.
So this one is, as you know, is we use the KT over Q, Ln, NC over ND. The doping is given. NC, this is a material parameter for the gallium arsenide. It will be given. And then using this equation, you can calculate this one. So using this one, you can calculate the VBR. Okay? Okay, so hopefully this way that I was able to finish on time. Any question you have?
Yeah, Professor, can you go back
Okay,
to the previous